All right, so we're going to take a look at question 72 to 81. It says last year the average grade was 78. This year we selected a simple random sample of 36 students and their average was 80. Suppose the standard deviation of all students who took the test was 4. So let's break down what we have here. Last year the average grade was 78. Okay, that's going to mean that mu equals 78. So this is kind of like what we assume to be true. This is going to be our null hypothesis. And then we took a simple random sample of 36. All right, so that means that n equals 36. And their average was 80. So this right here is our x bar. Suppose the standard deviation of all students, which means this is sigma, was 4. Okay, so this is standard deviation. So here we have basically we have our null hypothesis that mu is equal to 78. And we want to know if, based on our simple random sample this year, if it's different. So it says use a z-test for the sample mean to see if there is evidence to support the claim the average grades are different than 78. At significance level of 0.05. So our alternate hypothesis is that mu is not equal to 78. Okay, and this right here tells us we're going to be doing a two-tailed test. Okay, so the first thing we want to do is calculate our test statistic. So you can see here, actually I'll type this in. So z is going to be equal to, in the numerator you're going to have x bar minus mu divided by sigma over the square root of n. Okay, so you can see here that well, x bar was actually 878, but since it's different, oh, sorry, I was right. So x bar was 80, mu was 78. We get that from over here. Okay, the standard deviation is 4. Okay, so that comes from over here. And square root of 36, that comes from n. Okay. And so when we take 80 minus 78, we get 2. And then square root of 36 is 6. So we get 2 divided by 4 divided by 6, we get 3.00. Okay. Now, all these kind of problems lead into each other. So we already said what type of test we're conducting. We already said it was a two-tailed test. So remember that what we're doing is we're looking at this normal curve, and we compute our test statistic, which is 3. So it's two-tailed test. We use -3 and +3. And our p-value is going to be the area in the tails. And since it's symmetric, we just take the area in one of the tails and double it. Okay. So this is why it's a two-tailed test, is because it was not equals. Okay, two-tail. Okay, moving forward. Now he wants to calculate the p-value. So again, you could have done 2 times the right tail, which is z greater than 3, or you could have done 2 times the left tail, which would be z less than -3. And of course, we're using normal CDF. Our z value is 3, is our lower bound. And our upper bound, we could have picked probably 10, but we'll just keep it at 100. Okay. So this area and this part is the right tail. And again, we're going to double that to get 2 tails. And this is going to be the combined total. These 2 areas are going to be our p-value, which you can see is very small. In fact, rounded to 2 decimals is 0. Okay. So what is the statistical conclusion that alpha equals 0.05? Well, remember we're going to compare the p-value to alpha, and here the p-value is 0, 2 decimal places, and alpha is 0.05. So here it is less than it, so it's very likely to occur. Therefore, we're going to reject the hoe. Okay. All right. So now it says, if a 90% confidence interval for the mean was 75 to 81, would we reject the null hypothesis that the true mean was 78? So notice that 78 is in this interval. Therefore, we would fail to reject it. Okay. And the next problem says, if is a 95% confidence interval for the mean was 72 to 84, we reject the null hypothesis. So here we look at 85, and notice that is not in this interval, right? So we're here. Therefore, we're going to reject the hoe. Okay. And then here it says, if we wanted to be 95% sure, the average was within 3 points. So notice within 3 points, this is the error. Okay. How large a sample would we have to take? So we're looking for n. So if we take our error formula and solve it for n, 95% is going to tell us that z critical is equal to 1.96. Okay. That's right here. And then sigma over the error. So sigma is right here, and the error is 3. And then we just square that, and we round up, right? Ceiling function. So therefore, we have to take at least 7 people. Now it says we think the scores may be higher this year than last year. With a simple random sample of 36 students, will we have enough evidence to support this claim at a level of 0.01 significant? So now it says, what type of test is this? So we said higher this year than last year. Okay, so it's a right tail test because we have a null hypothesis, which says the scores last year were 80. Or no, sorry, they were 78. And now we're going to say the alternate hypothesis that we think mu might be higher than 78. So now this right here is greater than, is pointing to the left, or it's pointing to the right. So it's going to be a right tail test. Okay. So again, we want to know if it's going to be able to support this at a level of 10%. So notice the other numbers are the same. So our test statistics is the same, right? But now we're doing the right tail test, so we're not doing twice one of the tails, we're just doing the right tail, which we actually calculated before, but we did 2 times it, right? So now the p-value is just the 1 tail. So we use an upper bound. In this case, I used 100. It's out here somewhere. Might as well be infinity. And the area of this tail was 0.013, which again, to 2 decimal places is 0. So once again, the p-value is 0, and when we compare them, it's going to be less than or equal to alpha, so we're going to reject it. So now remember, the claim was that the scores are higher this year. So if you go back, so the claim was here, right? We think that they're higher. So since we rejected this, that means we're going to support the alternate hypothesis that they're higher. Okay, let's see if that was the last problem. All right.